Yeah, no, it's fine. So,
Is there a place to put this one?
yes, here. Okay.
Okay. Okay, so hello everyone, and it's a pleasure being with you today. And thank you for Marta for giving this opportunity to be with you today. Today I will be talking to you about test design and automation, which are two essential activities that are part of the software testing activities. Can you hear me? Is it working? Okay, perfect. So about me, so I'm not a morning person. You can say this, I think. And today I'm also feeling cold, so that's why you may not be able to hear me very well. So I recently moved from Canada to Iceland to join Reykjavik University as like assistant professor in the School of Computer Science, and also to join the CRIS Lab, which is the Center of Research and Engineering in Software Systems, which Marta is the director for this center. So we are a group of researchers that do research in systems and software at different areas. You have Gylfi and Björthorn, who they're working in database. Marta, which she works in human-computer interaction. Marcel, which works in sensor networks, and I work in cloud computing and emerging technologies. So the goal of my research is to revolutionize the application development so that it can tackle the industrial challenges that is associated with emerging technologies. And when we say emerging technologies, I mean things such as the Internet of Things, cloud computing, linked data. So I have now several projects that I'm currently running. Some of them, which is about how to architect cloud native applications and IoT applications. Another project is regarding and trying to answer how to automatically refactor monolithic application into microservices. And I also work on how to optimize linked data for query traversal, which is mainly how to optimize searching graphs rather than the normal way of searching data, the text, like through text mining techniques. So in addition to these projects, also I'm currently collaborating with several international projects in Canada. One with a company in Waterloo, where I work with them on social network analytics, and a lab in Montreal, where we work in software testing, which mainly like this lecture will be about. So this lecture, I know that you have an introductory lecture before this in software testing. So this will continue on what you already learned from that lecture. So we will talk about what we should test and how much testing is enough. So we should try to answer this question. And we will define some of the testing terminologies that related to software testing activities. So we will talk about something called model-driven test design. And in test design, you should, by the end of this lecture, be able to distinguish between what is test criteria, what test requirement, what is test specification, what is a test case, what is a test suite, and so on. You will see this through the lecture. And we will talk also about test automation. So let's start by a program like this. So you have a program which is a black box. You don't know what's inside, but you know that it has one interface, such as this, which is a function that takes two parameters, x and y. And those x and y, both of them are integers. My question is, how should we test this program? So yes, this is a question for you. It's insert strings. Yes, we may insert strings to test that this is not the normal behavior of the program, but we know that it's integer. At least we need also to test these integers. I mean, this is good. Like you are testing like the things on the boundary or on the edges that are not covered within this. So if we want to test integers, let's say we want to test the integers, focus on the integers. What the parameters, what inputs should we pass to this program in order to test all cases? Negative integers, positive integers, zeros. Yes, this is good, but is this enough? Can this detect the fault? Well,
does it return you anything? Or?
Well, yeah, it may return something. Let's say that this is void. It does not return anything, but it can return something. It should return something. Let's say it returns the, I don't know, any integer value. We don't know about it now. So this is a good question too. So see, now we start thinking about investigating this. So when you look at a program like this, you should look at it as being an investigator, and you have a crime scene, and you're trying to figure out all these aspects of this crime scene by uncovering all the links. So first he thought about, oh, can be cases outside this integer x and y and outside these parameters. Then someone here said, oh, we have to check for positive, negative integers. Then someone else said, oh, does it have like a return value? Well, and this shows you that just blindly try to test is very, very difficult. So we have to have more systematic way to analyze and cover this program. So we can look here and say, okay, we just want to test all possible values of integers, and all possible values of integers of x and y can be infinity. Someone else maybe think and say, okay, so what platform or what hardware this program runs on? And based on that, if you know that this runs on a computer that is 32-bit, have 32-bit registers, and the integer here will take 32-bit, then we have 2 to the power 32 for each values for each integer, and for both of them we have 2 to the power 64, right? Values. So this can be very, very hard, very complex. The number of test cases can be very large. For example, if inside this black box is something like this, if x minus 100 less than 0, then if y minus 100 less than or equal 0, then if x plus y minus 200 equal to 0, this is the only case that cause the crash. Of course, you will not write a program that crashes, but this is the case that will induce the crash. Then the only case that will generate this crash is when the input is 100 and 100. So both x and y are 100. So you have to have this exact value. So testing for one negative value, one positive value, and a 0 will not solve it, will not detect the fault. Testing for string will not detect the fault. The only case that will detect the fault is having 100 for input and for both inputs. So this is very difficult. The input space can be very large, can be infinity in some cases, and that's why even software giants such as Microsoft, Google, they still struggle, and they can't tell you that we can have a bug-free software. And that's why you see all these disclaimers and these messages, oh, if you use this software, we are not responsible of any crashes that happen to your application. You can see this in all kinds of softwares. So one of the things that all of you, I think, used, if you're using Java, for a long time, since the 80s, the Java implementation has a bug in something that every one of you using, which is the implementation of the binary search. Very simple implementation. Everyone implemented it this way. So I will not take the time because we already had lots of time wasted so far in trying to preparing everything, and I was late. So I will not waste the time to let you know what is the bug here. But the bug was discovered only in 2006 because the need for addressing and searching for a series or for lists and arrays with large numbers become more like everyone starts needing this. I will show you there. Yeah.
It's okay for you to take 45 minutes because we were supposed to have an open session afterwards. So
Okay.
you can just take your time.
Okay, perfect. So anyone can tell what's the problem in this. So do you know what's binary search? Okay, so you have an array, let's say, of numbers, then it should be sorted. Then we check the one in the middle. So because it's sorted, so we check the index in the middle. Then if it's the value we're looking for is greater than, then we just throw the half on like the first half and look at the second half, and we keep doing this. So it's of log n, like the complexity of it is of log n. So the order of it. So do you know what's the problem in this? So we have while low less than the length, we have the mid value, and we have the, so it's equal low plus high over 2, which is, I think everyone implemented this way, right? Okay, C++ is the same. Okay, so I will tell you the problem for now. So the problem is here, which is a correct implementation, but does not work when in one case. Do you know which case causes problem here? I just give you like a hint in the previous slide when I was talking about registers, hardware, 32-bit something. So if I have low plus high over 2, when I make low plus high, if I have two integers, big integers, both of them almost as like very large that they fill the whole, so bigger than half of 2 to the power 16. Okay? So when I sum them, they will be huge that they will not be fit within the register itself. So there will be an overflow. And this will cause a problem. So this sort will not work for, or this binary search will not work for what it's intended to work for. So the solution was very simple. Anyone can suggest solution. So once you know the problem, you can suggest solution. Yes, divide first. So if I divide this over 2 and this over 2, then I sum them, then this will solve the problem. Or if I say max or high minus low over 2 plus low, which is the same somehow, it's also solving the problem. So you can solve the problem in other ways. But you need to detect it first. And detecting it can be very complex. So testing is complex. Exhaustive testing means to be able to test all, like to go through all the cases, so and discover faults based on trying all inputs. Is this possible? Not possible. So complete testing is nearly impossible, and that's why and this is for several reasons. One reason is what we already mentioned before. The input space can be very large. It can be infinity. What's other reasons? The design. So the design issues may be too complex to completely test. So in the example, the first example we have before, we have this black box and this function, and it takes only 2 inputs. But inside this function, it may be also depending on some other variables that are not related to the inputs. It's related to the global variable in other parts of the program or in hardware or whatever that's coming from other parts of the system. So the design issues may be too complex. Also, it may be possible that it's not possible to also put the system in all execution scenarios. We see this when we ship a product. So in many cases, you ship a product, and after shipping a product, you discover faults. Why? Because you did not test in all environments. You don't know ahead of time all the testing environments that you have. And if your program depending on the system, then good luck. So the central issue in testing here is that giving something like this, the input domain and the program, so the input domain, all the input space and the program, we want always, of course, to execute this input and see the observed output and check that the observed output is similar to the expected one. So both are the same. So the problem, the central issue and what we want to achieve here is that, okay, is how to select a subset of the input domain in a systematic and careful manner so that a test engineer can deduce as accurate and complete as possible the properties of the entire program by observing the behavior of part of the program. Okay, and this is the essential idea of what we call test coverage. So we want to define some criteria, which we call it the coverage criteria, and based on these coverage criteria, we want to satisfy these criteria. Okay, which is also the core essence of what we call test design, which have a complete course that I'm currently teaching in software testing that mainly cover this point, which is only how to generate and how to generate this, like how to design tests based on test coverage criteria. And this, of course, the goal of this course is to turn you from what they call it testing monkey, which is also a term. It's not. So from testing monkey that trying all possible inputs by hand to a testing engineer that use systematic ways to discard some of these inputs in the input space, some of these test cases. Like I can say, okay, I don't want to test these because it's not important. Of course, you can't 100% assure that, but for this kind of testing and for this kind of coverage. So we talked at the beginning at what we call model-driven test design. So what is the process of model-driven test design? It starts by the software artifacts. What is a software artifact? Okay, I mean, what is the not files, but what are the parts of what are the different things that makes the program? So we have the program itself, which is the code, the executables, we have the design, we have the requirements, we have the configurations. So all these things part of the program. So when we talk about program artifacts, we're talking about all these things. Okay? So we have the software artifact, and the problems can happen at any of these. So it can happen at the requirement. So your engineer that goes and talk to the customers may not collect the requirements in a good way, or may miss something that, or your design engineer may miss how to implement or how to design or how to interpret what the requirement people like or what the analysts like convey to them. So they missed how to design it. Then, so the problem can happen at any of these artifacts. It's not at any at one stage. That's why we have different levels of software testing. At unit testing, like integration testing, system testing, and at higher level, we go to acceptance testing and so forth. So for software artifact, in model-driven test design, the first thing is to do two tasks at the same time. The first one is analysis, in which you create something called model structure, which is an abstraction of the software itself. So if you're talking about code, I may generate a graph, which is just control flow graph, how the execution is performed. Or I can generate from any of these artifacts, you can generate an abstract version of the application itself, of the software itself. And based on that, we have also the software artifact. We can focus on the test requirements that's coming from the domain engineers. And based on those two, we can set a test criterion, what we want to test, what we want to state a message about this software. Like, yes, I covered all the statements. I covered all the lines. I covered all the paths, the execution paths. I covered all the output values. So you say, like, you set your test criterion. Based on that, you have refined test requirements. So you say, okay, those are the test requirements that I want to satisfy. And based on that, you create something called test specifications. So we have two concepts here, or three concepts: test criterion, test requirement, and test specification. What's the difference between those three? So requirements, things coming from the end user. The criterion is what's coming from the test engineer. He say, okay, I want to cover this. So we have requirements, we have criterion, and we have something called test specs or test specifications, which are more formal way of putting the requirements into more concrete way. So the requirements can talk about the what aspects, and the specifications talks about the how aspects. So what need to be tested versus how it can be tested. We will see examples, concrete examples, so don't worry. So based on that, we generate input values. So these are the inputs for X and Y at the beginning. So we generate input values, and together we have, from the requirements or specifications, we know the expected output. So we have input, expected output, plus something called prefix and postfix, which are values that put the system, the prefix, put the system in the correct state and return the system to the correct state. Because we want to test it always from the same point. So prefix, postfix, expected value, and input, those are four things: input, expected output, prefix, and postfix. Those are what we call a test case. Of course, this test case for one scenario, one execution, we need many of them. We call this test suite. The test suite can be automated in a way that we write it a test script to execute it, and then we execute it, and based on that, we can get pass or fail. So either this test case pass if I get the expected output, or it fails if I did not get the expected output. Good. So we know now this. So let's say that, and based on that also, how many test cases we generate, we can satisfy the criterion. So if I am generating test cases to execute the program, my criterion is to cover all the statements. I covered 50% of the statements. So I get passed for all of them, but I covered 50% of my criterion. So I keep refining this until I get 100%. Or what? Or until I get tired. Okay? Or until I need more coffee, or until I need more, until my budget ends for testing, because you can't keep testing forever. You will never have a bug-free software. So there should be a stage where you say, okay, this is enough. I should ship the software. And put this disclaimer that if crash happen, it's your responsibility. Okay? So there's different reasons, of course, to stop testing and to say that, okay, it's time for shipping. But you have to satisfy the criterions. I mean, yeah. Okay. How you define a 50%? Okay. So let's say that I have a program. Let me wait. So let's have a program like this. If x greater than 10, print x, else print y, something like this. And this takes or x plus 1, let's say. And this just function that take x. So if my input here is 11, I will so how many statements I have here? I have 1, 2. So these are called statements. The other one are conditional statements. I mean, those are the executable ones. So if I have test case 11, and I should print 11, so this is my test case. So T1, the test case is 11, 11. Okay, so if I get 11, which is greater than 10, I will print this. So this is 1, 2. So the test criterion is to cover all statements, which is 2. I covered so far 1 over 2, which is 50%. Yeah, so based on the criterion. So each criterion have different, like you can say, based on statement, this is called the statement coverage test. So based on statement coverage, I achieve 50%. Now, I may achieve 100% on one kind of a criterion, but I can tell you, okay, based on path coverage, this is still 50%. So, I mean, there is different kind of criterions, and based on that, we. So, I think it's good because now you understand what's a criterion. So, testing activities, whenever I'm like they need a break, they can take a break. I don't know.
But won't you just want to finish and then we can take a break and have the open session just shorter, like 20 minutes? Is that okay?
Okay. So should I? So I will cover until test design. Then I will not cover the automation today. Just test design. It's good.
Okay.
Good.
But you, yeah.
I can't go through it very fast. I mean, it depends on what you like.
Yeah, I would actually like you to do that. So maybe it's better to take right now and then he will continue. Is that okay? Yeah. Good. Very good.
Good that we managed to.
Yeah, making it works. Yeah, that's right. So now it stops by itself, or how it works?
No, so we can either stop now, this, and I always do that actually. So
Yeah.
we should do that.